So imagine you're standing in the middle of a room and it's so loud that you actually need heavy-duty industrial ear protection just to, string a single thought together.
Right. It's a completely hostile physical environment.
Exactly. You are surrounded by these towering rows of hardware, and they're generating enough sheer thermal energy to literally melt steel if the systems around it fail for, like, even a few minutes.
It's a handful of minutes, yeah.
And that is the physical, highly sensitive, and frankly dangerous reality of the modern cloud. So today we are doing a deep dive into the exact document that dictates how you actually survive managing that kind of environment.
Which is an incredible document to look through.
It really is. We have our hands on the SuperCloud Composer, or the SEC Applications Logs User Guide. And specifically, we are analyzing Release 3.12.0, which was published in April 2026.
Yeah, and we should clarify right up front, this isn't just some standard software manual.
No.
For anyone operating at this kind of massive scale, this document is, well, it's the definitive blueprint. It's how you track the life or death telemetry of a modern data center.
Right. So our mission today is to unpack how IT professionals track, filter, and basically manage these truly massive streams of operational data because, that data is what keeps the digital world from physically combusting.
It's a high-stakes industrial operation. And honestly, treating it as anything less is just a recipe for catastrophic downtime.
Yeah, you can't just casually run these spaces.
Exactly. The absolute foundation of modern IT infrastructure,
Yeah.
the core belief you have to adopt when managing these environments, is that log collection is your only ground truth. It's non-negotiable.
Right.
It's a vital tool in understanding the actual operational state of your data center.
Right.
Without these logs, you're effectively flying blind in a warehouse packed with, hundreds of millions of dollars of hardware.
Which is terrifying.
It is. What the SuperCloud Composer software provides, and what this 3.1.4 manual outlines in such explicit detail, is the methodology for data center operatives to drill down through 3 highly specific levels of granularity.
And those levels are the component level, the server level, and the rack level, right?
Spot on. We are going to examine all 3 today, because the end goal here is always about enforcing governance, reporting on strict compliance standards, and just maintaining general serviceability across the entire fleet.
So if you ever had to parse, 1,000 lines of syslog during an active outage, you know the anxiety of trying to find the signal in the noise?
Oh, absolutely. It's a nightmare.
So we are starting our analysis at the absolute lowest, most granular level the SCC monitors, which is the BMC events.
Right, the baseboard management controller.
Yeah. And for those deep in the hardware trenches, the BMC is very familiar territory. The manual specifies that the SuperCloud Composer is capturing 2 things here: message event logs, or MELIs,
Yep.
and session event logs, which are SELs.
Which basically form the bedrock of all hardware diagnostics.
Right.
Because, the BMC is operating entirely out of band.
Right. I always look at the BMC as like the autonomic nervous system of the server.
I think it's a great way to put it.
Because it's an independent microcontroller, it's embedded right there on the motherboard, but it has its own memory, its own network interface, and crucially, its own dedicated power trace.
Yes. That power trace is key.
So even if your primary CPU has completely locked up, or the operating system is just kernel panicked and died, that underlying autonomic system is still pulsing, it's still watching, and most importantly, it's still logging.
And the data points the SCC aggregates from these BMCs are highly structured. The manual shows how the user interface breaks them down by severity.
And it categorizes those as, okay, warning, critical, or info, right?
Exactly. It extracts the specific message string, the device identifier, the physical location, and the BMC IP address, all neatly organized.
Now, the examples provided in the source text paint a very clear picture of what these admins are looking at every single day.
They do.
You have a critical alert reading, 12V upper critical going high. You have an info alert stating web logout was successful. And then you have a seemingly benign OK alert that just reads presence detected. But I want to push back on this a bit, or at least interrogate the logic here.
Sure, go for it.
Aggregating all of this into a single dashboard, like logging a massive 12-volt spike on a motherboard trace, makes obvious sense. You need to know that.
Right. That's a hardware failure in progress.
Yeah, but if you are aggregating logs across a deployment of, say, 50,000 servers, pulling in every single presence detected or web logout successful, doesn't that seem like a massive architectural penalty?
It sounds like it would be.
How does the SEC prevent these baseline, frankly boring logs from completely blinding the administrator during, say, a DDoS attack or a cascading hardware failure? Doesn't it just create noise?
It's a great question. And honestly, that tension between data volume and actionable intelligence is the defining struggle of observability right now.
Right.
Because it does seem counterintuitive to dedicate compute resources to processing an OK status. But those benign logs are the only way to establish a chronological baseline for pattern recognition.
Oh, I see.
In these complex distributed systems, a critical alert rarely happens in a vacuum. If you only log the failure, you only know that the system died.
But not why it died.
Exactly. You lose the temporal mapping. Let's map out that specific 12-volt example from the manual.
Let's do it.
If you just see a 12V upper critical going high alert, the voltage regulation module on the motherboard is failing. That's all you know.
Right.
If you don't have the preceding logs, you might assume it's just random hardware degradation, maybe a blown capacitor. And so you dispatch a technician to swap the board.
Which takes time and money.
But what if you look at the SCC dashboard and you see a presence detected OK message? And that is followed 10 seconds later by a web logout successful info message.
Oh, wow. Yeah.
Then followed precisely 1 minute later by that 12V critical alert.
Then you aren't looking at random hardware degradation at all.
No, you are not.
You are looking at a human intervention that triggered a failure.
You have established causality. Because what happened is someone physically approached the rack, which triggered the chassis intrusion or presence sensor.
Right, the presence detected log.
Exactly. Then they logged into the BMC web interface, made a configuration change to the power delivery settings, logged out,
Web logout successful.
and immediately spiked the voltage trace. So the SuperCloud Composer relies on those info and OK logs to reconstruct the narrative.
That makes total sense.
It transforms an isolated hardware failure into a fully auditable event.
And the manual actually details a specific UI feature to accelerate this exact kind of forensic work. Under the location column for these BMC logs, the SEC provides a clickable hyperlink.
Yes, the location anchor.
The source uses the specific example, QARack.5c, and clicking that specific link transports the administrator directly to the target system page, automatically highlighting the relevant event type for that exact node.
Which is huge. Think about the mean time to resolution, the MTTR in a crisis.
It's all about speed.
Exactly. When an admin receives a critical hardware alert, the traditional workflow involves, reading the BMC IP address, opening a completely separate DCIM tool.
Data center infrastructure management tool.
Right. Then they have to cross-reference that IP to a mass address, map that to a physical switch port, and then trace that to a physical rack coordinate on the floor.
Which takes what minutes you absolutely do not have.
Exactly. Clicking QARack.5c and instantly pivoting from a logical network view directly to the physical geography of the hardware completely collapses that diagnostic timeline.
It's immediate.
The software is anchoring abstract telemetry to concrete reality in milliseconds.
And that physical anchor is actually the perfect transition to the next layer of our analysis, because the primary byproduct of all that electrical telemetry we just discussed is immense, unyielding heat.
Heat is the enemy.
Always. High-performance computing has pushed way past the limits of traditional air cooling, and that moves us into the second category of logs tracked by the SuperCloud Composer.
The in-rack CDU events.
Right, CDU being the cooling distribution unit.
We are firmly in the realm of direct-to-chip liquid cooling here.
Yes, we are. The manual explicitly outlines telemetry tracking for EIA 250 kilowatts and OCP 250 kilowatts in-rack CDUs.
Which is a staggering amount of power.
Right. If you are listening to this and you've never stood near a fully loaded Open Compute Project rack pulling 250 kilowatts of power, you really have to understand the sheer thermal density we are talking about here.
It's hard to conceptualize.
You literally cannot move enough chilled air across those heat sinks to prevent silicon degradation. Fans won't cut it anymore. You have to pump liquid coolant directly over the processors.
Right, the thermal load is just staggering. When you concentrate 250 kilowatts of electrical draw into the footprint of a single rack, that hardware is existing perpetually on the razor's edge of thermal runaway.
And the alerts the SEC tracks for these CDUs really reflect that razor's edge. The source lists highly specific error states.
Let's hear them.
So we have alert emergency stop, alert CH1 external leak sensor error, alert facility pressure fall under alert level, and alert left pump 1 error.
Very specific mechanical failures.
Right. But what really caught my eye here is how the system ingests these errors. Because alongside the CDU IP addresses, the logs track specific trap IDs.
Yes, the SNMP traps.
The manual gives examples like 579, 522, and 699. And I look at these trap IDs kind of like the telemetry streaming off a Formula One car's engine during a race.
That's a really apt comparison.
Right, because we are tracking external leak sensors right next to high-voltage power planes. It's this stark reminder that the invisible abstractions of cloud computing rely entirely on high-pressure wet plumbing.
Literally wet plumbing mixed with high voltage.
Exactly. But structurally, I wanted to ask you, why rely on numerical trap IDs through the simple network management protocol?
Yep.
Because if the SEC is already aggregating text strings for the BMC logs, why use these rigid numerical object identifiers for the cooling unit?
It comes down to the interrupt-driven nature of mechanical failures. And, more importantly, the microsecond latency required to respond to them.
Speed again.
Always speed. Polling a device for a text-based log is computationally heavy, and it operates on a schedule.
Okay, so it checks every so often.
Right. If your management server pulls the rack every 30 seconds and a pump fails on second one, you have 29 seconds of thermal runaway before the management software even knows there's a problem.
Oh, wow. And at 250 kilowatts, 29 seconds of zero coolant flow.
Means you're replacing melted hardware. The silicon is fried.
That's incredible.
Exactly. So a trap ID is a push-based mechanism, not a pull.
Okay, so it sends it out proactively.
Right. The moment the CDU controller detects a pressure drop, say trap ID 522, it fires that tiny, lightweight integer directly to the SuperCloud Composer immediately.
And numbers are faster than text.
Way faster. Computers parse integers vastly faster than they parse variable length text strings. The SEC doesn't have to read facility pressure fall under alert level, analyze the string, and determine a response.
It just sees 522.
It receives 522 and instantly triggers an automated sequence, which might involve halting computational workloads on that specific rack, ramping up secondary pumps, or even initiating an emergency power-off to save the silicon.
So the logs in this specific context, they are not really historical records at all. They are active, automated tripwires.
Yes. They are the immediate mechanical reflexes required to manage that F1 engine, to use your analogy.
Got it.
Because if you lose facility pressure, the coolant stagnates. And that specific tracking of the alert left pump 1 error shows the granularity of the redundancy.
How so?
Well, if the left pump fails, the trap fires, the SEC logs it, and the automation ensures the right pump immediately takes the load.
So the system stays online.
Exactly. The admin auditing these logs the next day isn't looking to see if the hardware survived. The automation handled that part. They're looking at the trap IDs to schedule preventative maintenance on the failing pump before the redundant backup also dies.
That makes so much sense. Okay, so scanning out from the individual rack, the thermal management challenge becomes exponentially more complex.
Because the heat has to go somewhere.
Right. The heat isn't just an isolated incident anymore. It becomes a literal fluid dynamics puzzle for the entire server aisle. Which brings us to Section 3, the in-row CDU events tracked by the composer.
Yes. These units manage the coolant flow and heat exchange for an entire row of racks simultaneously.
And this is where data center management really seems to shift away from traditional IT and move straight into the realm of applied sciences.
It's pure physical science at this level.
Absolutely. The alerts detailed in the SEC documentation for in-row CDUs basically blur the line between IT and chemical engineering.
They do.
The manual highlights two specific traps here. We have trap 83, which is a turbidity over range, high alert, and trap 79, which is a pH over range, high alert. Now, I have to play the astonished outsider here for a second. Wait, why are we testing the pH level and the turbidity of the internet?
I know, right?
Are we managing a server farm or a swimming pool?
Honestly, we are essentially treating the data center like an integrated chemical plant. Because it fundamentally is one.
It's wild to think about.
The fluid loops circulating through an in-row CDU are the actual lifeblood of the deployment. Let's examine the physics behind trap 83, that turbidity alert.
Okay, turbidity being the measure of suspended particulate matter in the fluid, right?
Correct. We are tracking the optical clarity of the coolant. High turbidity means you have microscopic solids. So gunk, biological growth if the biocides fail, or most critically, shaved metal flakes.
No, flakes.
Yeah, and they are circulating at high velocity through the plumbing. Remember the direct-to-chip cold plates inside the racks we just discussed?
Right, the ones sitting right on top of the CPUs to absorb the heat.
Exactly. Now, to maximize thermal transfer, those cold plates aren't just flat blocks of metal. Internally, they have these microscopic channels milled into them to drastically increase the surface area interacting with the fluid.
Oh, okay. I didn't realize that.
Yeah. So if your in-row CDU is reporting high turbidity, those suspended particles, those metal flakes, will eventually reach those microchannels and act like a microscopic logjam,
Oh, wow. They bottleneck the flow directly over the absolute hottest component in the system.
which creates a severe localized thermal event.
Mm.
The server literally cooks itself, even if the main pumps out in the row are showing perfect pressure.
Because the fluid just can't get through the blockage.
Exactly. Now, correlate that with Trap 79, the pH over range alert.
I really wanted to dig into this one because a pH drift in an isolated water loop is a nightmare scenario for facilities teams.
It really is.
If your coolant loops mix different metals, say you have copper cold plates mixed with aluminum heat exchangers or stainless steel manifolds, you are setting the stage for galvanic corrosion.
And the pH level of the dielectric fluid or the treated water is the only thing keeping that corrosion in check.
Right.
If the pH drifts past the acceptable baseline, so if it becomes too acidic or excessively alkaline, the fluid actively begins stripping ions from the metal surfaces.
Oh man, so it is literally eating the plumbing from the inside out,
Exactly, which introduces metallic flaking into the coolant.
which subsequently triggers your turbidity alert.
You see how it connects?
It's a vicious, self-reinforcing cycle of hardware destruction.
Yes, it is.
And what fascinates me here is how the SuperCloud Composer unifies this telemetry. Because historically, your IT administrators would be sitting in an NOC staring at network packet loss and CPU utilization metrics, right?
Right. Isolated in their own software world.
Well, a completely separate facilities team, probably in a different control room, would be monitoring water chemistry.
Exactly. Silos.
But the SEC aggregates this chemical telemetry right alongside the BMC hardware alerts. It provides a unified ingestion engine for all of it.
It forces a holistic view of the infrastructure.
Which is necessary.
Completely necessary. If a server is thermal throttling, the admin, using SEC, doesn't just blindly look at the server fan speeds.
Right, they look at the whole picture.
They can pivot to the in-row CDU logs, see a historical drift in the pH levels over the last 3 weeks, followed by a recent turbidity over range alert, and intelligently deduce that the microchannels in that specific server are likely clogged with corroded metal.
That is incredible. It bridges the gap between digital processing and physical chemistry in one interface.
It's the only way to troubleshoot at this scale.
But that thermal energy, once it's extracted from the row, it cannot be destroyed. Thermodynamics won't allow it. It can only be displaced.
Right, you have to move it out of the building eventually.
Exactly. This requires moving the coolant outside the white space of the data center, which shifts our operational dashboard out to the macro facility level.
The big stuff.
Yeah, Section 4. The SEC documentation outlines specific tracking for sidecar and cooling tower events.
Where you're tracing the heat all the way up to the atmosphere.
And the documentation reveals a really distinct shift in the search parameters at this scale.
How so?
Well, when we analyzed the BMCs or the in-rack CDUs, the logs were indexed by highly localized identifiers. So we were looking at specific device names or localized CDU IP addresses.
Right, very narrow focus.
But once you move to the cooling towers, the search fields in the SEC interface pivot to facility name and facility IP.
You are stepping out of the microenvironment of a single rack and into the heavy industrial infrastructure that keeps the entire building operational.
The architectural scope that this one application covers is just staggering to me.
It covers everything.
You can track a granular 12-volt discrepancy on a single processor trace, and then within the exact same UI navigation tree, you are monitoring a massive industrial cooling tower venting megawatts of heat on the roof of the facility.
It's a massive shift in scale.
I'm really curious about your read on how this macro visibility impacts incident response times, specifically regarding what people call the domino effect of cascading failures.
Oh, the domino effect is the primary cause of extended outages in heavily siloed organizations. Let's break down a scenario.
Please do.
Let's say a massive fan motor burns out on a roof-mounted cooling tower. The tower loses its ability to efficiently reject heat into the ambient outside air.
Okay, so the tower is crippled.
Consequently, the facility water returning to the data center floor is, let's say, 3 or 4 degrees warmer than the required baseline.
The baseline shifts and the heat essentially starts backing up into the system.
Exactly. That warmer facility water hits the sidecar heat exchanger on the floor, which then struggles to properly chill the secondary fluid loop running to the in-row CDU.
It's cascading down.
Right. That fluid, now carrying excess heat, flows to the in-rack CDU, which triggers a temperature warning trap. And finally, the processor itself cannot shed its thermal load
And that's when the BMC on the motherboard throws a critical heat alert.
and potentially shuts down the node.
Wow.
Huh.
And if your teams are siloed, the IT admin only sees the server dying.
Right. They spend hours swapping motherboards or checking OS workloads, completely oblivious to the fact that a giant fan belt snapped on the roof.
Because it's not in their dashboard.
Exactly. While the facilities team might know the fan is broken, but they don't realize it's already causing critical hardware failures on the floor because they don't have access to the server logs.
So the SuperCloud Composer shatters that barrier.
It provides a true single pane of glass. An admin can look at the logs, see the BMC heat alerts clustering across multiple racks. Then, they quickly query the cooling tower logs using the facility IP.
They see the root cause immediately.
They see the macro failure, and they can coordinate directly with facilities to route the coolant to a backup tower before the cascading failure drops the entire application stack.
That visibility is priceless. Okay, so we've traced the operational telemetry from the silicon out to the roof. But managing the physical byproducts like heat is really only half the battle.
The other half is usually us, humans.
Right. We have to examine the electrical input, and more importantly, the architects making the decisions. We are moving into section 5 of our analysis, focusing on power and the human element.
These are arguably the most unpredictable variables in any deployment.
Because hardware generally behaves according to the laws of physics.
Human operators, however, introduce entirely different vectors of risk.
Exactly. Now, the SCC manual handles the electrical flow through PDU events power distribution units, but the documentation heavily emphasizes two specific human-centric logging categories.
Activity and all tasks.
Yes, and the text draws a very deliberate line between them.
It's an important distinction.
Activities are defined as giving global admins visibility into transactional day-to-day activities. Conversely, all tasks track overt user-initiated events. The manual explicitly lists actions like deploying an operating system or allocating pooled resources such as GPU or storage volumes.
That structural separation is absolutely vital for auditing and compliance framework.
If I were to map this conceptually, I'd say the activity logs act like the continuous security camera footage of the data center.
Okay, I like that.
They are tracking the passive transactional hum of the software environment, right? Automated API calls, routine database syncs, just the background noise of the system.
Right, the routine stuff.
But the all tasks log is the dispatcher's ledger. It is intentional, highly privileged action.
Yes.
Because if a production environment suddenly goes offline because an experimental operating system was pushed out over a live cluster, we need the cryptographic proof of exactly who pushed the big red button.
And the manual explicitly references governance and compliance reporting as a core driver for these features. Because in modern enterprise IT, plausible deniability just does not exist.
No, it can't.
When a mission-critical workload fails, the postmortem analysis cannot rely on human memory or assumption.
People misremember or they lie.
Exactly. So you interrogate the logs. Did the liquid cooling fail? You query the CDU logs. Did a breaker trip under heavy load? You check the PDU events. Did an administrator accidentally run a destructive script against a production storage volume? You pull the all tasks logs. It provides an unalterable chain of custody for administrative actions.
I really want to zero in on the exact example the manual used for user-initiated tasks. It mentions allocating pooled resources such as GPU.
Which is extremely relevant right now.
Right. If you look at the current landscape of AI-driven architecture, GPUs are the most highly constrained, fiercely contested resources in any data center.
They are the economic engines of the modern data center.
They are staggeringly expensive. Their power draw requires massive provisioning, and as we discussed, they generate those intense thermal loads.
So tracking exactly which user is allocating those cool GPUs is paramount.
Exactly. Because if a developer allocates a massive GPU cluster for, I don't know, a shadow IT project, or maybe they just fail to deallocate them after a machine learning training run finishes.
The cost isn't just a slight bump in the utility bill.
What is the cost?
The cost is multifaceted. First, obviously, you have the raw financial burn rate of the hardware itself running at maximum draw.
Which is thousands of dollars an hour.
Easily. Second, you are starving legitimate priority business applications of the compute they need to meet their SLAs.
Right. The resources are tied up.
And third, you are keeping that 250 kilowatt rack running at thermal maximum stressing the CDUs and the cooling towers completely unnecessarily.
Oh, right. The wear and tear on the cooling infrastructure.
Exactly. So by strictly logging GPU allocation in the all-task view, the SuperCloud Composer acts as a strict governance enforcer.
It holds people accountable.
It allows the global admin to perform immediate financial and operational audits. They can claw back those stranded resources and identify exactly which user account is violating the provisioning policies.
So the software essentially evolves from a simple hardware maintenance dashboard into a really critical financial and security tool.
It has to at this scale.
But aggregating this level of granular detail brings us to a massive practical operational hurdle, which brings us to Section 6, the janitorial work of big data.
Yes. The data bloat problem.
We have discussed millions of logs generating continuously.
Millions per hour, really.
Right. Every BMC presence detection, every CDU pressure drop, every macro facility shift, and every human API call. The sheer volume of telemetry creates immense database bloat.
It does.
So how do the watchers manage the weight of their own data?
It is the ultimate paradox of observability platforms, honestly. You require absolute data retention to perform forensics.
Yeah,
But excessive data retention actively degrades the performance of the tool itself.
that makes sense.
The system chokes on its own history.
And the SEC manual dedicates significant space to the janitorial realities of log management. Across all these categories, it outlines standard UI functionality: reload, display, and search.
Basic database interactions.
Right, and it details how the search mechanism utilizes strict ND conditions across multiple fields.
So you're stacking filters.
Exactly. For example, filtering by a severity of critical and a specific device identifier and a specific timestamp to really narrow the query.
Just standard Boolean logic applied to database queries.
But then the documentation addresses the export and delete functions. The UI allows administrators to export or delete by selection, by filter, or globally delete all logs.
The dangerous buttons.
Very dangerous. And situated directly above the delete instructions in the manual is this massive pink caution box.
I love the pink box.
The text reads verbatim: caution log entries will be permanently purged and unrecoverable. Be sure to archive log data in advance.
The pink box of doom.
Seriously.
In technical documentation, when the authors use bold colors and the word unrecoverable, you know you are dealing with catastrophic operational risk.
Which begs the question, and I really want your take on this, why provide the mechanism to permanently delete this telemetry at all?
What do you mean?
Well, enterprise cold storage is remarkably cheap today. You can provision petabytes of archival storage for a fraction of the cost of the compute hardware. So why would a platform actively encourage administrators to perform permanent, unrecoverable purges of vital system data? If a compliance audit requires a look back at a hardware failure from 3 years ago, deleting that data is a massive liability, right?
It would be, yes. But this comes down to the fundamental difference between raw storage capacity and active index database performance.
Unpack that for me.
Yes, dumping raw text files onto a cold storage array is extremely cheap. But the SuperCloud Composer isn't just storing text files. It is actively indexing hundreds of millions of database rows to enable those complex multi-field A&D searches we just talked about.
The indexing.
Maintaining those indexes in active memory or even on high-tier SSDs requires massive computational overhead.
So it's about query velocity during an active incident.
Precisely. We have to view this entirely through the lens of incident response.
Okay.
Imagine it is 3:00 a.m. A critical in-row cooling loop just dropped pressure. Cascading thermal alarms are filing across under racks. The administrator, half asleep, logs into SEC to find the root cause.
They need answers immediately.
They need the UI to render instantly. They need to run a complex filter across BMCs and CDUs, and they need that query to return results in milliseconds.
Right.
If the active database is bloated with 3 years of irrelevant presence-detected logs and routine web logouts, that search query might take several minutes to resolve as the engine churns through billions of dead rows.
And as we established earlier, at 250 kilowatts a rack, a 3-minute database query means
The processors have already melted. The hardware is dead before the search bar even finishes loading.
oh, wow, that puts it in perspective.
That is exactly why the manual emphatically instructs admins to export and archive before purging. You don't destroy the historical record. You move it to that cheap cold storage to satisfy your compliance audits.
Right, the archive handles the legal side.
Exactly. Then you ruthlessly purge the active database to ensure the SuperCloud Composer remains lean, responsive, and capable of saving the infrastructure during a real-time crisis.
You're basically clearing the active workbench so you actually have room to operate.
That's a perfect analogy.
And the primary tool the SEC provides for managing both that targeted archiving and the incident response itself is the start date, end date calendar filter.
Which is arguably the most powerful forensic tool in the entire interface.
Because when a catastrophic failure happens, the one variable you almost always know is the timeline. You know the exact minute the application went offline.
Usually, yeah, the monitor starts screaming.
Right. So the calendar tool allows the admin to build a temporal fence around the incident.
Temporal fence, I like that.
If the outage happened at 10:15 p.m., you set the start date to 10:10 p.m. and the end date to 10:20 p.m. And because the SEC aggregates everything into that single pane of glass, you can slice horizontally across the entire infrastructure stack within that specific 10-minute window.
You pull the BMC logs to see the hardware failing.
You pull the CDU logs to see the pressure dropping.
You pull the facility logs to check the cooling towers.
And the task logs to see if a human operator triggered the event.
You reconstruct the exact chronological sequence of the disaster across multiple disciplines. And you do it without having to correlate timestamps across 5 different proprietary software tools.
It functions as an operational time machine.
It really does.
So, synthesizing this entire analysis, the sheer scope of what this single piece of software accomplishes is pretty remarkable.
It's massive.
We started our deep dive looking at a tiny microcontroller logging a web session.
The humble BMC.
Right. And we followed that thread down into the microscopic chemical realities of coolant pH and turbidity.
The metal flakes in the microchannels.
Yes. And then out to the massive industrial fluid dynamics of roof-mounted cooling towers. And finally into the rigid governance of human operator tasks.
It acts as the central nervous system. It translates the chaotic physical realities of heat, pressure, and electricity into structured, actionable digital data that human beings can actually comprehend and manage.
It completely reframes how you conceptualize cloud infrastructure.
It grounds the cloud in physical reality.
It really does. So I want to leave you with a final thought to consider.
Right.
The next time you open your laptop or execute a massive database query or even just stream a 4K video, don't just envision your data bouncing seamlessly through invisible networks.
There's no magic cloud.
No. I encourage you to think about the intense, high-stakes physical environment making that request possible. Think about these silent SNMP traps firing in milliseconds.
The turbidity sensors guarding against microscopic metal flakes.
Right. And the tiny 12-volt BMC monitors making billions of micro-adjustments to ensure the silicon doesn't combust. Because somewhere out there, in a deafeningly loud, incredibly hot warehouse, systems like the SuperCloud Composer are working overtime to ensure the physical world supporting our digital lives doesn't literally melt down.
It's a massively complex, deeply physical machine, kept perfectly in balance by the data it generates.
Thanks for diving deep with us.